So far, we have looked at inverse dynamics control, both in joint and in task space, but we were only interested in motion of the system. Now, in this video segment, we move on and use this technology in order to also control the interaction of the robots with their environment. Robots that are interacting with the environment have a pretty long history. What I show you here is a very famous video by the group around Osama Khatib in Stanford, was like investigating this field of force controllable robotic systems, of operational space control, of interaction between robots and humans already quite some time ago. What you see here are industrial robot arms that are retrofitted with end effector force torque sensors, and they're used for various household tasks. And the speciality of it is that, like in some directions, these robots typically control the position, while in other directions, they are regulating interaction forces with the environment. There's several examples of that where this is pretty useful. For example, if you have a robot that is hovering your environment, obviously this robot has to produce a motion in XY direction while it produces certain force in Z direction. So it's a hybrid task. Similar things happens if you're interacting with the machine. If you clean a table, also here you're wiping, you're moving in X and Y, you're doing the rotation with the end effector, but you're not producing, or you're actively regulating the force in Z direction. The same here for ironing, where you have to create a very precise pressure force in Z direction and move in the other directions. So what this group came up with is so-called operational space control, which is kind of a generalized formulation or generalized framework that allows you to control both motion and force. So let's have a look again at this robot arm on the right hand side. Now this robot arm for certain task, for example doing a task along this wall, it has to move in a constrained fashion, so only in certain directions, while in other directions it has to produce a contact force. That means the end effector force that the system has to apply is composed of a part that contributes to a contact force and to a part that contributes to an acceleration in the motion directions. So in other words, I can extend now this end effector dynamics that we have derived before with these contact forces. So we have had this formulation, so lambda times end effector task space acceleration plus mu plus p equal to these task space forces, and we have green, which is the motion, and what we add now on top of that, since certain directions are force controlled, is a contact force. Now since we are living now in task space, there is no Jacobi transpose mapping, because like we're defining a task directly such that we have this contact force acting on our system dynamics, and all of that has to come from this end effector force. Now typically we have, as we see in the example, certain directions where we can only produce force but no motion, and other directions where we can move but we cannot really regulate the forces. So what we can do is we can include so-called selection matrices. So we have a selection matrix which ensures that the end effector acceleration is really in the direction where the system can move, and we have another selection matrix which ensures that the forces we want to apply at the contact is really only in the direction where we can apply the contact force. And then we get Fe with this. So what we see here, this part in here, this is nothing else than Fe, and if we pre-multiply it with the Jacobi transpose mapping, we get the desired torque that we have to apply to our system. So you see here the complete controller. These selection matrices can be found in the way that we are defining a 1 if something can move, and we're defining a 0 if something can't move but it can apply a force. And this is of course in a end effector frame. So if you look at this end effector frame here, which is aligned with the task, we can easily define that in z direction we can apply a force but no motion, while in x and y we can define motion but no forces. However, if you have to transform this now to a world fixed frame, what you have to do is you have to rotate between this contact and world frame, and for this you have to pre-multiply it with the rotation matrix transposed and post-multiply it with the rotation matrix in order to get the selection matrix. And you have to do this both for the position, which is position and force selection matrix. So we have the position, which directions can I control the position, versus this one is essentially the selection matrix in the direction I can control the forces. So this is essentially for the forces. Do the same thing also for the rotation. So there's certain directions where I can produce a rotation and other directions where I can produce a moment, and also these ones we are mapping through this C transposed sigma C. It's easiest if you look at this with a couple of examples. So what you see here on the right hand side is a gripper that holds a block on a flat ground, and what we want to identify is the selection matrix for the motion in position direction, for the force in position direction, for the motion in rotation direction, and for the force in rotation direction. So how can the system move? The system can move in X, it can move in Y, it cannot move in C, but it can apply a force in C. In other words, if I look at the motion sigma, it can move in X, it can move in Y, but it cannot move in C direction. On the other hand, if I look at the thing in the rotation direction, I immediately see that I can rotate around this axis. However, I cannot rotate around this axis, and I can also not rotate around this axis. So I have zeros here and a 1 here. If I look at the forces, as I said before, we can apply a force in C direction, and we can apply a moment around the X and around the Y axis as indicated here. Second example is inserting a cylindrical peg in a hole. And again, like you want to figure out these sigma matrices, selection matrices. What is here important is we can move in Z direction, we cannot move in X and Y direction. We can rotate in this direction, so around the Z axis, but we cannot rotate around the X or Y direction because the hole is pretty long. And that should immediately allow you to set up these selection matrices. So which direction can we move? Only in C, so that's the only one that has a 1. Which rotation direction can we move? Only in C, so that's the only one that has a 1. And the forces are either 1 minus sigma of the motion, or you immediately see it also because you can apply a force in X and Y, but you can't apply a force in C, and similar to that also in rotation direction. So let's apply this to a little more complex system. We have here a two-link example, and what we give you is the dynamics equations of motion in joint space, so as a function of q double dot. And we ask you what is the torque such that the end effector, which is connected or at this wall, produces a certain acceleration along the wall and produces a certain force into the wall. What we have to do for figuring this out is that step 1, we have to transform everything now to task space, and for this we of course need to have the Jacobian at that point. So we need to have the position vector to this point, and then from this position vector we can directly calculate the position Jacobian through partial differentiation. And that allows us to then identify lambda, mu, and p. which are only a function of these known parameters up here, and the mapping with j plus some term which has a j dot in there. And then we are applying the operational space control formulation that we have seen before. Namely, we have to multiply it with Jacobi transposed. In here we have the end effector force, which is given by the acceleration part plus mu plus p plus the contact part. Now you might ask, what the hell are the selection matrices in here? Now the selection matrices are implicitly in here, so we have here a selection matrix for the motion, and we have here a selection matrix for the forces. But the motions that we have here are already defined in a way that Sm times r dot double dot is equal to r double dot. So this is already consistent with the wall that we have here on the sign, and the same for the force. So if I take my Sm, take this in green, so my Sm is, I can move in y direction, but I cannot move in x direction. And if I multiply Sm with this r double dot, I will again get r double dot. Now to conclude this video segment, we again go back to our excavator example. We give you generalized coordinates, equations of motion, and end effector position rotation Jacobian. And the questions that we want you to answer is, first one is that you are filling this bucket with a horizontal acceleration of -1 meter per second squared and a drag force of 1000 Newton, while producing additionally 1000 Newton of normal contact force. So what that means is that you're producing here a normal force on the ground, and at the same time you have a drag force that acts on your system while you're filling. And the question is, what is the joint torque?